today is the last chapter or last section of chapter 3. So dilations. This is the transformation that we talk about that is not an isometry. So based on knowing that something's not an isometry, tell your neighbor what you know about it.
It's not isometry, then it's not going to be. Yeah.
Hey, volunteer. If it's not an isometry, what do we know?
It's not the same size, but it's the same shape.
Good. It's not the same size, but it's going to be the same shape. Okay, so for instance, this piece of paper right here that I'm projecting, this piece of paper is not the size that you see on the projector. I know. Some of you have been confused all this time. You thought that this piece of paper was this size, but it's not. Okay? This is this a reduction or an enlargement? An enlargement. Okay, so I'm kind of helping you define some things here. Okay? That's what a dilation is. A dilation is something that is reduced or enlarged. Okay? You take an object, you make it smaller, or you make it bigger. Okay? So it's a similar figure, reduced or enlarged. Similar, remember, means all angles are still the same. They look the same. Okay? It's just one's bigger and one's smaller. It's like having a mini-me, you know? A little mini-me. Okay? All right. Scale factor we'll talk about. Transformation, similarity transformation. That's what a dilation is. It's a similarity transformation that changes size. It doesn't change shape. Okay? Same shape, different size. That's what a similarity transformation is. All right. So why don't you go ahead and look at those definitions, put down what you need, read over that example, answer question 5 with your groupie there. We'll take a few minutes to do. All right. So let's try some of these. Can I borrow your book real quick? Thank you. Just real quick, there's what you're looking through, but number 5, what scale factor produces enlargements? So if I want something to be the exact same size and not reduce or enlarge, what do I multiply it by?
1.
By 1. Yeah, it's a 1-to-1 ratio. How many knew that? Okay, this is that participation thing again. Okay, what scale factor produces enlargements? Diamond?
Would it be anything greater than 1?
Anything greater than 1. So what produces a reduction? Be careful with this answer. Not that I'm discouraging you. Emily?
Something that's less than 1?
Yeah, less than 1 but greater than 0, right? Something that's less than 1 but greater than 0 is a reduction. All right? And when you start multiplying things by negative numbers, you get some really cool looking things happening there. Example 2, if you read about the person, did anyone read that? That's kind of weird. So if you read about scale factor in people, it's kind of crazy there. All right, but we're not going to go into that anymore. So every dilation, make sure you make a note of it. Every dilation has a center and it has a scale factor. You need to know where its center is, and you need to know what its scale factor is. Okay, if you don't know where you're projecting from, then that's a problem. Like if I was projecting this paper up onto the big screen here, if I don't have my center of projection, the place I'm projecting from, then we never see it. We have to have a center, somewhere where we're zooming from. Okay? All right, so let's go ahead and take a look at completing a dilation as a whole group. If you turn your sheet over, on the back of your note page today, you should have that shape. Okay? It says dilate triangle RST from point C using a scale of factor 2. Then we're going to dilate it from point C using a scale of factor of 1/4. We're actually going to change this one over here. We're going to change the scale factor. I don't want to use the same scale factor, so let's make this a 3. I'm pretty sure that'll fit, and we'll make this one 1/2. Okay? So there we go. Sorry, I know that's kind of small to see there. Let's start with this together, okay? Dilate triangle, RST, from point C using a scale factor of 2. The first thing you need is if you don't have a straight edge of some sort, you need to get one. That'll make this a lot easier. Okay? You have got the rulers that say butts are gross. Don't smoke. Okay? Public service announcement. Yeah. Okay. All right. I'm going to use my bright ruler here. Okay. Now the first thing you need to do when you're doing a dilation, you need to start at the point, your center point. In this case, they're telling you you're going from C. So remember, every dilation has a center. Here's my center. And then I have a scale factor. Here's my scale factor. Okay? So we're centering at point C with a scale factor of 2. That means from point C, you are projecting this figure. It's enlarging because it's greater than 1 from point C. So what I'm going to do is I'm going to lightly sketch a line through each of my vertices. Now, my line, the line segment I'm sketching here, it doesn't have to be extremely long. However, it has to be long enough that I can duplicate the distance from, say, C to S, from C to R, from C to T. I need to duplicate that. In fact, I need to double it, right? So when I'm measuring that distance, and I'm going to use centimeters here, and you guys can use what you want, but mine looks like it's about, from C to R, about 3.4 centimeters. Okay, so I'd have to go 3.4 centimeters, which puts me about right there-ish. There-ish. I'm kind of at a weird angle because I can't get my head under the document camera, but okay. And then from C to S, mine appears to be about 4.7. Okay, good. So from S, we will measure out 4.7, which brings me about there-ish. I'm not sure that there-ish is a word. However, it's okay to just make it up right now. All right, 2.6-ish. So out from T, we'll go 2.6-ish. That is right there. So we have T prime. We have S prime. And we have R prime. And then I connect them. So R to T. R to F, or T to S, excuse me. And R to S. All right, and so now you've dilated your original triangle by a scale factor of 2. For some people, it helps to see it easier if you shade it. You don't have to, but some like to shade it. Like, oh, there it is. Okay. Kind of pops out there a little more. And plus, then you get to practice your coloring. All right. You notice a few things, like my eyes catch when I'm grading your dilations, my eyes catch that this line, RT, is parallel to R prime T prime. That ST is parallel to S prime T prime. That RS is parallel to R prime S prime. Everyone see that? That's a good way for it to do a quick check. If you're like, that just doesn't look right, usually it's one of your lines isn't parallel, which means one of your points is off. Okay, any questions on it? Everyone show your neighbor your dilation there. You can brag, it's all right.
Mine's great. I was like, I exactly the same. Yeah.
Okay. Any questions? Hey, let's do a quarter. Now, I'm not going to measure this time. I'm going to estimate a little more. So if I'm going a quarter from C to R, a quarter is, hi.
I thought you changed it to more than a half.
I changed this one down here to a half. Okay, this one we're going to still do a quarter. Okay, so if I'm doing a quarter is half of a half, right? So if I'm going from C to R, I'm going to take half. That looks like about half. And I'm going to take half of that half, which is right there. That's going to be my R prime. Now, I don't always let you do estimation like this, but for a dilation, I'm going to allow it as long as you can estimate appropriately. Now, when I say a quarter, I want a quarter. I don't want a half. So if you have to measure to get that, because you're like, I always mess it up, then measure. But I took half, and then I took half of a half. I know this is a quarter. That's going to be my C prime prime.
If you have to measure.
Half to measure, yeah. That wasn't meant to be, but good thinking. That's good mathematical joking right there. And half of a half, some of us have to measure. That's good. Good stuff. That just means that goofy math jokes are rubbing off. That's good. All right, and then half of S looks like about right there-ish. And so a quarter about there. Now you're going to find out really fast how good your estimates are based upon parallel lines. So when I connect these, if I'm looking, this line should be parallel to this line. Looks pretty parallel to me. Okay, this line should be parallel to this line, and it looks like we've got it. And then C prime, T prime, prime, that's a lot of primes, should be parallel to R, or do I have the wrong point? Oh, I labeled that C, it's supposed to be R. Unbelievable. There we go, there's a rookie mistake. All right. So now we have our little mini-me triangle. Show everyone your mini-me triangle. Oh, isn't that cute?
There's mine.
It kind of looks pretty cool when you start seeing that progression like that. At least I think it does. All right, how many got it? Okay, tell your neighbor how it changes when you go down to these. What changes, other than the numbers? Did you tell Olivia? All right. Hannah, what changes? Good, you're dilating from R, so we're now pushing out from this point right here, which means our figure now is going to project out this way, right? So if I'm going a scale factor of 3, the benefit is you only have to duplicate 2 points, right? So if I'm going scale factor of 3 and measure that out, I want everyone to go ahead and project that 3 times as big right now on your paper. Then hold up. I'll be walking around. Well, here. So I have from R to S, looks like about 2.5. Okay, so I need to go 2.5 out. Well, actually, I need to draw my line through that first. So 2.5 times 3 is 8.5. Thank you. 2.5, 2.5. No, 7.5, right? 2.5, 2.5, 2. Yes, let's go 7.5. All right, right there. And then looks like 3.5, 7, and then we need to go out to 10.5. Do I have enough? Oh, I do. Good. Shoo. All right. So this is T prime, prime, prime. This is S prime, prime, prime. Usually, we won't be doing so many on the same. So our shape. There we've got it. Now once again, should be about parallel. Looks like it is. So you can kind of see the new big triangle. And the big triangle actually includes a lot of the small triangle there, right? Isn't that cool?
Yes, I had it just chilling.
And we go half. Half brings us there. So that's S prime, 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 prime. Too many primes, man. Then to there, T, 1, 2, 3, 4 primes. And that's our dilation of 1/2 right there. Okay. Everyone rate themselves 1 to 5. Okay. All right. They're amazing fun. Okay. Tell your neighbor 2 things you've learned today so far. Your assignment, example side exercise is 1. Find the scale factor for the dilation that maps the solid. Know where you're going from. You're going from solid to dashed. So you've got to first ask yourself, if I'm going from solid to dash, you got to ask yourself a question that will help you figure out your scale factor. Work with your groupie. You get a minute. Okay. Hey, from solid to dashed, greater than or less than 1? Go ahead, Emily. Less than 1. How do you know?
Because it's like splitting up the 2 fours, and like if you added the 4s, that would be 8, but then 1 minus 4 and 1 minus 4, so you have half.
Good. So yeah, you cut it in half, right? You got smaller. From solid to dash, you got smaller. We went from, as Emily said, 8 to 4. So my scale factor could either be 8 to 4 or 4 to 8. Those usually are the 2 answers I get. Which one is it? One of those is wrong. Grace, which one? 4 to 8, which is 1/2, right? Why isn't it this one?
Because it's going from the solid to dotted, so then it's like going down, it's getting reduced.
Yeah, it has to be less than 1. It can't be 2. That's 2 right there. So this is our answer. Okay? So when you're getting smaller, the number is less than 1. Okay? Solid to dash, getting bigger or smaller, everyone?
Bigger.
Bigger. So my length here of a side, this is 2. Everyone tell your neighbor what this is, and then what your scale factor is. Okay, this length is? 6. So from 2 to 6, are we going 2 to 6 or are we going to 6 to 2? 6 to 2. It's getting bigger. Scale factor is 3. Because it went from smaller to bigger. It enlarged, right? So if it's an enlargement, your scale factor has to be greater than 1. This would be 1/3, which means it would be getting smaller. Right. No, you're measuring here. Yep. So that's a length. That's at -1, and you're going to 5. Good. Other questions there? Okay. I want you to take a look at example 2. Example 2. For each pair of figures, determine whether one is a dilation of the other. Explain. Go ahead and work with your groupie. Okay. Number 4. Hey, are they dilations? No. And if you look at your scale factors, in order for something to be dilations, your sides have to be proportional. Okay? That means they have to have the same scale factor. So 4 is to 4 as 6 is to 10. Is that true?
Nope.
No, they're not equal. These are not dilations. And this is a valid reason why. That's a mathematical reason why. Okay? Are these dilations?
Yes.
Yeah. If we compare 3 to 6 and 5 to 10, they both have a scale factor of 1, or in this case, this is 1/2. So if we're going from here to here, okay, they both reduce to 1/2, right? They're the same value. That's a true statement. So this is a dilation. Oops. Okay, so compare them. They have to have the same scale factor, or they have to be proportional. Now, I guess you could have said 6 to 3 and 10 to 5 if we're comparing this one to this one. Either way, it was fine. Okay, questions there? All right, last piece is matrices today. Now, we didn't talk a lot about matrices earlier in the year because we stopped discussing things. Okay, so this, for some of you, is going to be new, especially if you didn't study up on that section. Okay, so right now, in order to do matrices, a matrix is where you set coordinates into brackets like this. In advanced algebra, we do a whole chapter on this. We have our x, y values, and then we have our points, A, B, C, D, up here, our vertices. Okay. So the coordinate for A is negative 2, 0. When we put that into our matrix, it looks like that. Our coordinate for B is 0, 4. We put that into our matrix like that. Coordinate for C, 2, 0. And coordinate for D, 0, negative 2. Appreciate you checking me though. That's good. Okay. Now, if I'm doing a dilation, one of the cool things in dilations is you can do what's called scalar multiplication. If this is my scale factor, all I need to do is take my matrix and multiply it by 3. This would be problem 10 here. I do what's called scalar multiplication. I'll zoom in on that now. Well, I don't even use the picture. Okay. All I do is I multiply each one of these things that's called an element. I multiply each element by 3. So 3 times negative 2 is negative 6. 3 times 0 is 0. 3 times 2 is 6. 3 times 0 is 0. 3 times 0 is 0. 3 times 4 is 12. 0. And negative 6. Okay, so my new figure, A prime, B prime, C prime, and D prime, are at those coordinates. Or the ordered pair, A prime is negative 6, 0. B prime, 0, 12. C prime, 6, 0. And D prime, 0, negative 6. Okay. Sometimes you'll be asked for it in ordered pairs. Sometimes they'll just say you can leave it in a matrix. If they don't specify, then you do which one you think is more valuable to what you're doing. Okay? There we've got it. If I'm doing scalar multiplication for a half, tell your neighbor how that would be different. Okay, how's that different if I'm doing scalar multiplication for a half? Hilton? Yeah. Good. Each one of these is going to cut in half. It reduces. All right. Your assignment is the mixed side. Okay, we won't do the example side. Okay, if you did more on the example, good. You got a little extra practice, but the mixed side is our assignment there. There you go.